I'll begin with a word of prayer. Heavenly Father, we thank you for this day. Again, Lord, I thank you for these students, for the weekend that's about to start. Just pray that we'd be able to glorify you again, Lord, in what we do this day. In your name I pray, Lord Jesus. Amen. So I was kind of halfway through this at the end of last class, and I don't want to reinvent the wheel here, so let me just kind of use the projector here for a bit. I am so we're talking about the first isomorphism theorem of linear algebra. I say of linear algebra because there's also first isomorphism theorems of other things, all right, like group theory or whatever else. And so the point is we take a linear transformation and its quotient map with respect to the kernel. So, and we can the result here is that we can make this mapping T bar, so-called induced mapping, and V mod W. Now W is the kernel. I just get tired of writing kernel T everywhere, okay? And so this mapping, implicitly defined by as follows: T bar of composed of pi is equal to T. Well, that defines an injection. In particular, the formula is this: T bar of x plus kernel is equal to T of x for each x plus kernel in the quotient by the kernel. Furthermore, the quotient space of V by the kernel of T is isomorphic to T of V. This little furthermore bit, this little moreover bit, is what we often use. When we use the first isomorphism theorem, often we find ourselves using this last little bit. It's very useful. I'll show you today. All right, so I showed you last time that this is well defined. In other words, despite the apparent dependence on the representative, it in fact doesn't matter. So we did that last time. The next thing to show is that T bar is a linear transformation. So if you take x, y, and v and c in the field, T bar of this plus that, by definition, is this. How do I know that this is equal to that? Well, I'm just using what? The definition of the addition of cosets, which says we add the representatives, right? Add the representatives. Then I use the definition of T bar, which was that T bar of that is just T of the representative. All right, that's the next step. Then I use linearity of T to pull out the C and break up the sum, all right? And then I just go back, because that is exactly C of T bar of x plus w and T of x y plus w. And there you have it. That holds for arbitrary cosets and constants. Consequently, we have that the T bar is in fact a linear map on the quotient space, all right? What's next? We need to show it's injective, right? That's the claim, that this T bar mapping is injective. So the question of injectivity, what you want to do then is you want to look at two cosets, x plus y and y plus w in the quotient space, two cosets here, and suppose that they have an equal output. So T bar of x plus w is equal to T bar of y plus w. Well, by definition, that means T of x is equal to T of y, right? But what does that mean? That means that T of x minus y is equal to 0. Aha! If T of x minus y is equal to 0, that means that x minus y is in the kernel, right? But that proves that x plus kernel t is equal to y plus kernel t, which is to say that if they have equal outputs, they have equal inputs. In other words, it's injective. So there you go. T bar is an injection. Finally, the isomorphism. Well, the isomorphism of V mod the kernel T is just given by this other mapping T prime. All I do with T prime is just to swap out before this had a U here, so I'm just replacing U with T of V. There might have been points in the vector space U which we didn't hit under the image of T, right? But if I replace U with T of V, then it's pretty much automatic that we're going to hit all the points in here. But here's the proof anyway. So if you take a point, T prime of x plus kernel T is equal to that, which is equal to that. That's the definition of T prime. Fine. If you pick any point in the image, like y is equal to T of x, then it's easy to see that x plus the kernel of T maps to y. But that point was arbitrary, therefore T prime is a surjection. So we have a injection and surjection from the V mod the kernel of T to T of V. Consequently, they're isomorphic, right? And there you have it. All right. So with that, I will excuse Excuse me. I seem to have somehow gotten sicker. I don't know what happened, but oh, thanks. So bear with me today if I say unusually stupid things. I'll try not to be too stupid. Let's see here. I think I managed to get through that department meeting we just had without saying anything too terribly offensive, so it's good. Always a win. All right. I know nothing, I say nothing. Let's see here. So, example. So just to, I want to, yes, sir.
Just a quick question. When is mission 9 due?
Wednesday.
Wednesday?
Yes.
Okay.
I can make it Monday.
Next.
Wednesday seemed more reasonable though, because I'm still working on the last half of it. Although that should be up today.
Okay.
Yeah. Some of those problems are pretty easy. Everything there looks much harder than it is. I really mean that this time. All right. And please, when I say use technology, use technology. There's one of those problems, all you have to do is write down the matrix for the quadratic form, feed it into the eigenvector, eigenvalue, the website I gave you guys a link to, right? It will spit back out to you the numerical eigenvalues, right? All you do is you take those, you go to the theorem I wrote right here, which was that the quadratic form looks like what? Lambda 1, x 1 bar squared, plus lambda 2, x bar 2 squared, plus lambda 3, x bar 3 squared. You take those numbers you found on the website, lambda 1, lambda 2, lambda 3, you put them there, you write it down. That is the solution to that problem. It's literally that. You did that? Oh, okay, good. So an example. V cross W mod W is isomorphic to V. Why is this true? Consider the map. T, a mapping from V cross W to V. How do you define this? T of x comma y equals to what? Was that? No. Brett with 2 T's has no answer. How about Audrey with 1 Y? Any answers?
Sorry, no.
No. As opposed to the less known spelling of Audrey with 2 Y's. But there's got to be somebody somewhere, probably in a commune. Let's see here. Definitely a Bernie Sanders supporter. Let's see here. I think you just want x. I mean, that's kind of like it. You might ask me, where did this come from? I can't really answer that for you, you know. But there it is. That's a mapping that goes from the Cartesian product of V and W to V again. All right, I've had enough. Go on, scoop. See? I'm very nice. I just do this. It usually works. All right. I'm removing all the comments from my brain that I shouldn't make right now. All right, they're removed. All right, let's go on. So what's the kernel of T? It's things of the form what? 0, comma, y. Schnikes. I guess that's not quite right. Oh yeah, I can't read my own notes. I'm missing something. This is equal to what? This is 0, Cartesian product with W. Right? So I'm missing I'm supposed to have a 0 here. Otherwise, I'd have to do more. I don't want to do more. Okay, so we have a linear map. Is it clear T is linear? It's clear T is linear. T is linear. This is its kernel. By the first isomorphism theorem, oh, by the way, is T a surjection? Is T onto V? This is clearly a linear surjection. It's onto. You pick a point in V. Pick any point you like. 7. If x is an element in V, then x comma 0 maps to x. Right, there you go. Anything in V we can easily cover. So it's a linear surjection. Therefore, in fact, V, in other words, V is actually equal to T of V is my point, V cross W, all right? Rather. So, by the first isomorphism theorem, we have that V cross W mod the kernel of T, which is what? 0 cross W, is isomorphic to V. Yep.
In the first line where you have your example written, just the red lettering that 0, does that have any difference to what you originally wrote, or like is that supposed to be?
Well, yeah, because the other, I think it's also true that V cross W mod W is isomorphic to V, but I don't know what that means. That's the thing is I don't know. I can only mod by a subspace, right? I haven't described how you would take the quotient with something else. We only have described the quotient for a subspace of a vector space, right? So W technically isn't a subspace of V cross W. But 0 cross W is a subspace, which is, it is true that 0 cross W, right, is isomorphic to W. That is true, all right? But it's not the same as W. They're different point sets. One I have defined the quotient for, the other one I have not. So there's that example. Another example we can look at is this mapping S. It's a mapping from, say, Rn by n to Rn by n, defined as follows. S of, let's say, x is equal to x plus x transpose. All right? If you have x, let's say if you have A equals to A transpose, if you have a symmetric matrix, then if we set x equals to what? I think if we set x equal to 1/2 A, we'll get what? Which is just what? A again, yeah? So what's that say? Can I put that in the words? What does that say about the mapping S? S maps to any symmetric matrix, right? Any symmetric matrix you like, I can find something, an n by n matrix, which maps to it, right? How would I know that the range is equal to, I guess that, in other words, I've proved what? Like symmetric, so what does that say? That says that, I can't, stupid, also, you can easily see that S of x transpose is equal to what? S of x, right? If you take the transpose of this formula, you get it back again, right? So you put those two things together. In fact, we have that the range of S, right, the image of S, the range of S, or in other words, S of Rn by n is equal to what? Instead of n of this, let's say this is the symmetric n by n matrices, right? Would you guys agree? The image of this map is the symmetric n by n matrices. If you divide this map by 2, it's what I usually call the symmetrizer. The symmetrizer map, it takes in a symmetric matrix and it just spits it back at you. But if you feed the symmetrizer an anti-symmetric map, it's 0. Oh, okay, so what's the kernel of S? Can we calculate the kernel of S? What's the kernel of S? By the way, this is what? Linear. I think it's clear that's a linear map, isn't it? By properties of transpose. The kernel of S is what? This would be x in n by Rn by n, such that what? Such that x plus x transpose equals to 0, right? So what is the kernel of S? The kernel of S is exactly the antisymmetric matrices, right? So you could say that this is equal to, let's say, AN, antisymmetric n by n matrices, right? All right, so now we use the first isomorphism theorem. What do we got? What does it tell us? If we feed this data to the first isomorphism theorem, what do we get? We get R n by n, right? Mod what? Mod the antisymmetric matrices, right? Is isomorphic to what? The symmetric matrices, right? So in other words, if you can think of visualizing Rn by n as like a plane or something, I mean, however you want to think of it in your mind's eye, if you take all the symmetric matrices, right? Excuse me, if you take all the antisymmetric matrices, rather, and you sort of glue them together, all you're left with, in some sense, is symmetric matrices. Like, that's all that's left. I don't know if that's a helpful image, but there. Maybe it's not. Another example. Actually, first, before I get to the example, I need to tell you a little proposition. If V is the direct sum of two subspaces, say A and B, then V mod B is isomorphic to A. This kind of looks like this first example I did, but it's actually different. All right? See, saying V is the direct sum of A and B, that means that both A and B are subspaces. I'm assuming, of course, here that A and B are subspaces of V, all right? So A is a subspace of V, B is a subspace of V, and what else do we have? We have A plus B is equal to V, and what does this circle mean? It means they're independent, right? So A intersect B is what? 0. That's all, I mean, that's implicit within saying V is the direct sum of A and B. Or you could say internal direct sum to be more precise. Okay, so what? We need a mapping that we can apply the first isomorphism theorem to, right? Remember what we had in terms of our, we had this, right? If X is an element of V, then there exists unique A and B such that what? A plus B, right? We had that was the structure of a direct sum. So given that, you can define a map, right? Because it's a unique A and B, right? So like define T of X or T of A plus B equals to what? I want this to be a mapping that I can use the first isomorphism theorem, right? So what I'm looking is for t that's going from, say, V to A. So which one of these do I want to keep? Just keep A, right. In the same way over here, I took x, y, and I kept x, right? Difference being this is a sum, whereas that was a pair. All right. So clearly, T of V is equal to A, right? So that much we can see immediately from this formula, right? Any A you pick in V, and rather any A you pick in A, you can map A plus 0 to it, for example, right? Or just T of A is equal to A, fine. And then what? We need to calculate the kernel. What's the kernel of T? So that would be what? That would be x in V such that T of x is equal to 0, which is just what? Right. So to be more precise, let me write it out again. A plus B such that T of A plus B equals to 0, right? But what's T of A plus B? T of A plus B is A, right? So this gives me A is equal to 0. In other words, this is really just what? It's precisely B. Yeah. People who use this theorem don't usually write this stuff out. They just say, it is clear that the kernel of this mapping is B. All right? Hence what? Thus, by first isomorphism theorem, what do we got? V mod kernel of T is isomorphic to B, aka A direct sum B mod mod B is isomorphic to A. I think we have earlier proved, right? By the way, I believe we have proved before that Rn by n is the direct sum of A, Sn and An, right? So you can see this also as an example of that theorem, right? All right, I'm gonna get the projector back out here for a minute. Thanks. One of the homework problems I'm assigning you guys, instead of doing A plus A transpose, I've given you A minus A transpose, or X minus X transpose, and asked you to work it out. It's almost the same example we just went through. It's just instead of having plus in the mapping, you have minus. So the roles of A sub n and S sub n flip over. But that should give you an example that you can understand in a nice homework problem. All right. And if you didn't understand what I just did, maybe that'll help you understand it, okay? All right. Now, that's not one I've published yet, but I will later today. Okay. So this is a differentiation operator, right? And well, here I've said it's for polynomials with real coefficients, right? But in fact, this calculation here just makes sense. You can replace the word polynomial with smooth function, and you'd be fine, right? You can define the derivative from a smooth function to a smooth function by differentiation, right? And what's the kernel of the differentiation operator? Well, the kernel of the differentiation operator is just the constant functions, right? So if you take the smooth functions mod the constant functions, then you're left with something where the differentiation operator becomes an injection by the first isomorphism theorem. And so like, let's see here. So I define, down here I actually have, oh man, I've still got the psi mapping. I should really make that d bar to be consistent with what I changed notation in the notes, and I haven't fixed this example yet, sorry. I'll have to fix it. To be in concert with what I was doing over there, I should really have d bar instead of psi. I had psi for d bar before, sorry about that. So like d bar of the equivalence class containing f, which is the coset, all right? The equivalence class is the coset. Oh, that's something I haven't emphasized enough in here. These cosets, they partition the vector space. And so if you give a given vector in the vector space, it's in one and only one coset. And the union of all the cosets gives you the whole space back again, right? So it forms a partition, and there's an equivalence class structure there. I think this is explained pretty concisely and decently in Curtis in the section I asked you to read, 26. But anyway, getting back on track here. So this is essentially d bar, all right? So d bar of the coset of f of x is defined to be the derivative of the representative. And that becomes an injection, right? Because if you have this is equal, then you get the derivatives are equal, right? Well, if the derivative of two functions are equal, and if x is taken from a connected domain, what does that mean? It means that they differ just by a constant, right? Remember we learned in Calculus 1, if the derivatives match, it's f of x is equal to g of x plus a constant. So that is exactly to say that they represent the same equivalence class of functions modulo constants. So in that sense, in this context, you get that the differentiation operator is injective. And so you can invert differentiation if you don't work with functions, if you work with equivalence classes of functions, right? And so in fact, that's, when we say differentiation and integration are inverse processes, sometimes we're talking about definite integrals, right? But to make good on that statement for indefinite integrals, you have to be thinking about equivalence classes of functions, right? So if you want d dx of the integral to give you back the function, and if you also want the integral of the derivative of the function to give you back the function, if you want both of those, then you're not really talking about functions. What you're talking about are equivalence classes of functions, because differentiation destroys constants. You can't get it back, right? And so this is an attempt at doing that carefully, because of course this is always true, right? The derivative of the integral of f is f. I mean, fine, that's true, right? That's just that's really the definition of the antiderivative, right? But this over here means that the integral and the derivative, they aren't really inverse functions, are they? They're almost, but they differ by this. There could be a constant that you're off by, right? So if you say that this thing and that thing are really the same thing, then that's an honest to goodness equality, right? And that's exactly what you get on the quotient space of functions modulo constants. The other place where this structure comes up is in the study of differential equations. I've got another example here, and I'll try to be quick about this, but if you study the linear differential equation L of y equals to g, right? The way people think about this in systems theory is they think that the L is fixed, it's a system, right? It's like a bunch of springs or something. And then g is a force that you put on this system, all right? So you got your physical system, you put the force on it, that's like the g. And then y is how the system responds. So we write this as L of y equals to g, but if you're a systems analyst, you think of this as g is the input and y is the output. All right? Now that only, to make sense of that though, more precisely, you should really think about the solution in two pieces. It's the homogeneous piece and it's the particular piece. The homogeneous piece goes to 0. The particular solution gives you back the forcing function, right? And so if you want to make this an invertible process, what you have to think about is that all those homogeneous constants have to be treated as if they're just 0. So what you do is you don't work on the set of solutions. You work on the set of solutions mod the homogeneous solutions. You treat all the homogeneous solutions as if they're the same thing, and in so doing you obtain an invertible map, not on functions, but on equivalence classes of functions where they're they're the same up to a homogeneous solution. Anyway, if you've taken differential equations, if you read this carefully, it'll make sense to you. If you haven't, don't sweat it, right? I mean, this is differential equations, not a prerequisite here. I am merely saying this to reach out to those of you who are either taking it or will take it. In the same way, I make comments about geometric vectors in R3, right? Because I know not all of you had Calculus 3. But in the past, I have, oh my goodness, this theorem. I'm not going to do this in class, but if you read this, it'll make sense to you. If you have W as a subspace of V, and V is finite dimensional, the dimension of the quotient of V and W is the dimension of V minus the dimension of W, right? And here's the proof, in short. Basically, what you guys tell me, what do you think the basis for the quotient space should be? Here's what you do. Take a basis for W, all right? Extend it to a basis for the whole space. Everything that was in the basis for W will become 0 in the quotient, because that's what the quotient does, it sets W to 0. Everything that's left is the part that's genuinely the extension. Those are the representatives for the cosets that form the basis for the quotient space. It's just that. That's all this proof says. So that's exactly the dimension of V minus W. That's how many linearly independent cosets you get in the quotient. And that's what this proof says in detail. I mean, they're details, but you got to prove linear independence of the basis and junk like that. It's not. I have made this a homework in previous years. I could delete it from the notes, make it homework again. You're like, just leave it like it is? Okay. Oh, I'm plumb out of notes. All right, let's see here. Can you hit the lights again for me? Thanks. All right, so I hope I've said enough that you guys see what the first isomorphism theorem says, and at least a little bit about how you can use it, right? You might ask, wait a minute, it's the first isomorphism theorem? Does that mean there are more? No, you guys never seem to ask that question much anymore. But in fact, yes, there are more. There is a second isomorphism theorem, and in fact, even a third isomorphism theorem. I'm not going to tell you them now. Just saying. There's also in section 26, I'd like you to read 26. I'm not going to go over this in class, but I'll let you read it. He also describes how if you have a linear transformation that goes from a vector space to another, and you have a particular condition on the subspace, I think it has to be invariant, then the matrix, and if you pick a basis for the subspace and then extend to the whole space, so it's like a basis which respects the subspace, there's this really neat, simple relation between the matrix of the linear transformation for the whole space, the matrix of the linear transformation for the subspace, and also the matrix for the linear transformation on the whole space mod that subspace. It's really simple. Like the one block is the matrix of the transformation restricted to the invariant subspace, and then the remaining block is actually the matrix of the linear, the induced map, the T-bar, the quotient map. So there's a very, and if you go back and look at some of the theorems we had in terms of eigenvectors and stuff, it'll kind of nicely weave together with that. So anyway, I will give you a hopefully simple. There's an example. There's an explicit example in Curtis. I'll try to make an example like that for you to do in the homework so you understand his example better, okay? But hopefully not too hard. All right. That brings me to our next topic, which is that of dual space. The dual space. What's that? Dualism? We don't like dualism? No? Oh. I don't know. I think I'm probably a dualist. I don't know. And let me not get into it. Dual space. Here's the deal. If V is a vector space over F, then V dual is simply the linear transformations from V into F. That's it. That's the dual space. It's the set of linear functionals on V. That's it. Let's see here. Let's think if we can think of any examples of dual vectors. How about this? What if we look at t of f of x equals to the integral from 0 to 1 of f of x dx for, let's say, continuous functions on the closed interval 0 to 1. So the integral makes sense, okay? Is that linear? Yes, the integral is linear. That is true. Is it outputting a real number? Yes. This then shows you that t is an element of, let me call this thing v. So t is an element of v dual. All right. By the way, what I'm currently describing is called the algebraic dual. As you study infinite dimensional vector spaces, it becomes important to distinguish between the algebraic dual and other duals. Like you end up looking at just continuous linear functionals or bounded linear functionals. And well, that's a larger story to have when you're talking about infinite dimensional things. If you want to learn more about infinite dimensional vector spaces, I would recommend Roman's Advanced Linear Algebra. That's a good place to read careful comments about infinite dimensional vector spaces. And it should be a fairly accessible book for you once you're done with this semester. Okay, so that's an example. Can you think of another example for me? How about trace? If we look at the trace, which is a mapping from, say, Rn by n. Oh, I guess I could do F, right? We don't have to do just R. We can do any field we like to F. How's that defined? Like the trace of A is what? Sum I equals 1 to n of A I. That's linear, right? It goes from the vector space. So basically this is I mean, the trace is an element of, I can't make up my mind, f n by n. Sometimes I'm trying to keep it real, other times I forget. So there we go. So the trace is a so-called dual vector, or if you like, of the n by n matrices. All right. Okay, so definition. If beta equals to v1, v2, vn is a basis for v over f, okay, then the dual basis, beta upper star, equals to, and you know, I'm going to use this notation, and I'm sorry if it's confusing to you. I hope it doesn't confuse you, but it is dangerous. If you don't like it, you can use a different letter with a subindex, but those are not powers. Those are just labels, all right? So sometimes it's useful to use labels which are upstairs rather than downstairs in this part of the material. This is a good place for that. This is the so-called dual basis. The dual basis for V dual, defined by linearly extending. What do? You linearly extending the following rule. Vi of Vj is equal to Kronecker delta Ij for all I and j, 1, 2, all the way out to n. This is the so-called dual basis. It's now, does that define, I mean, I call it a dual basis, right? But is it actually a basis? I mean, just because you call something a basis, does it make it a basis? I haven't proved it's a basis, have I? I gave you a definition for it. Is my definition reasonable? Why would this be a reasonable definition of VI, a mapping, right, from V to the field? Is that enough? Why is that enough? Because beta is a basis, right? And we proved earlier, if you define a function on a basis, then there's a unique linear extension off the basis to the whole vector space, right? So by construction, my V upper I are linear. That's done. It remains to show what? That you can write any dual vector in terms of a sum of these things, and also that they're linearly independent. So let's try to understand that. How can you write any dual vector in terms of the dual basis? So I usually use alpha for a dual vector. Let alpha be an element of V dual. All right. Consider x, and in this material, it pays off to write x like this. Sum I equals, well, I say j equals 1 to n of x upper j, all right, v lower j. So this is a convention that I use when we're doing things with dual spaces. I put the components up for a vector. That's not x to the j power, that's just a label that's upstairs, okay? So, what happens when we act alpha acting on x? What do we get? Indeed. Alpha is a dual vector, right? So it's a linear function of vectors, which means I can do what? Pull out the sum, right? And I can pull out the numbers, x upper j, and what does that leave me with? Alpha of vj. All right. Man, what to do about this then? That's not quite productive yet, is it? What is x upper j, though? I forgot to prove a little lemma. Sorry about that. Here, I'll do it up here. So, vj of x, with x so defined, all right, is equal to what? It's in fact equal to x upper j. I'll show you the proof right about now. So, okay, so vj of x is equal to vj of what? Of the sum of x upper j, v, oh, I'm sorry, let me use an I here. X upper I, v lower I equals 1 to n. Pull out the sum. You got x upper I, v upper j, v lower I equals 1 to n, which is what? By definition, v upper j acting on v lower I is what? It's a dual basis, right? By definition, that's the Kronecker delta. This here is the Kronecker delta ij. As I've told you guys before, the Kronecker delta is the natural enemy of the finite sum. It kills it. And so that leaves you with what? I is the dummy index of summation. J is a free variable, a free index here. So you're left with the j. That leaves us with x upper j, which is precisely the content of my little lemma. Right? Now, why does that help us? In the black. Something like that. I can use the little lemma down here, right? I mean, this is what? This is xj. This is actually what? This is actually v. I'm sorry. This is a number, right? So put the number first. Alpha of vj. That's just whatever alpha gives you back when you feed it vj. That's a number, something in the field. And x upper j, though, that's actually v upper j acting on x. But by the definition of how we add linear transformations pointwise, right? If you add, what's the sum of transformations? I mean, how do we add? Long story short, if you study what it means, how to sum linear operators together, you can put parentheses like this. In fact, it's this transformation acting on x, which is to say what? If that's true for all x, right, in the vector space, that allows us to extract from this an operator equation, an equation about linear functionals, namely that alpha is the sum of alpha acting on v lower j of v upper j. J equals 1 to n. What's that say? That says that if you give me any dual vector, I can give it back to you in the span of the dual basis, right? In other words, the dual basis is a generating set for v dual. That's half of it. Now we need to prove linear independence, right? How do you prove linear independence of the dual basis? So you're looking at v1, v2, vn. That's beta dual. Consider in the usual way c1, v1, c2, v2, cn, vn equals to the 0. This 0 is the 0 function, right? This is the 0 function. This 0 actually is the 0 function from v to the field, by the way. This is a sum of transformations. Don't be fooled. It's not just vectors. So what can you do? You want to show what? You want to show all these constants are 0. You guys tell me what to do. This is just like the orthonormal discussion we had. Remember orthonormal basis? How did we show orthonormal implied linear independent? What do we do? There are actually some very strong analogies between this material, what we're doing right now, and the orthonormal material. The way it works is very similar. So much so that sometimes people use the same notation for both. So this, you just do what? How about this? Act on v sub I. What's that give you? Zero acting on vi, well, that one's easy. That's 0 by definition of the 0 functional. And all these other ones are 0 as well by definition of the dual basis, right? 0, 0. Everything's 0 except for this, which is what? 1. So therefore, we get that ci is equal to 0 for all I. Therefore, beta dual is linearly independent. So we have linearly independent spanning set for the dual space. It is indeed a dual basis, which I think is kind of neat that it's that simple. Well, maybe you don't see it as simple yet, but trust me, it's simple. So you could define things, right? Like here, the annihilator of W. So let W be a subspace. W a subspace of V, right? The annihilator of W would be this. It would be alpha in V dual such that what? Annihilating. What do you think this should be? Sending, and what should it send to 0? Alpha of something, let's say little w equals to 0 for all what? Not a trick question. I'm going to put you out of your misery. W, big W. If we had more time, someone would have said that. Oh, you did say, I'm sorry. I'm sorry, Jess. I should have heard you. Oh, well. Too many voices in my head. What can I tell you? So that's the annihilator of W. It's a subspace of the dual space, right? And in fact, you can show that this is in fact a subspace of V dual. All right? And you know what else? The dimension of W plus the dimension of the annihilator of W is equal to what? Does this remind you of anything? Doesn't this look just like if V was an real inner product space? Doesn't this remind you of like W perp? So that's V and V such that what? The inner product of V and W is equal to 0 for all W, right? And what do we have? We have W direct sum W perp is equal to V, right? So of course the dimension of W plus the dimension of W perp should be the dimension of what? V. Guess what? Dimension of V, yeah. True. However, I can't say this here, right? That wouldn't even make sense over there because W is a subspace of the vector space, but the annihilator of W, it's in the dual space. So I can't really form a direct sum of those. If you read Lang's linear algebra, Lang, in fact, Serge Lang, in fact, uses this notation. In Lang, he doesn't talk about the annihilator. He just calls this thing the perp. But he then also works out things for much more general inner products than we've worked on, so-called non-degenerate scalar products, which includes other things like Minkowski space and more awful things. Anyway, we'll pick up. I have much more to tell you guys about dual spaces. There's also a double dual space, and when we really study how the dual spaces interacts with the inner product space structure, some very nice things happen that we'd like to understand called the musical morphisms. There's something called the flat mapping and the sharp mapping, and all sorts of other punny things happen. So I will shut up. Thanks, guys.